Thank you, Ali. A few weeks ago, I was cleaning up my office, some old stuff, and came across a memo that I think bears to this presentation. It's an internal memo that I wrote back in 1990, addressed to George Barnes, Sushil Arora, Francis Chung, Bill Smith, and Ron Thomason. For those of you who know those gentlemen, they were either in the management or the modeling group of CWRSIM. Title of the memo was Linking CVGSM with DWRSIM. So that was over 25 years ago, where the thinking of linking the simulation model C2VSim with, or CVGSM at that time, with the systems model DWRSIM at that time originated. And actually Francis was the one, because he knew that I was interested in going for my PhD, and he said, why don't you use that as your PhD topic? So, the problem was, by the way, the four techniques that I outlined there, two of them had to do with a depletion analysis, two had to do with direct and indirect linking between the two models. I didn't pursue that approach because it still wasn't clear to me how do you link the two. So when we moved over to CVSIM1, that was just a mapping of the depletion analysis. There was no CVGSM. When we went into CVSIM2, I developed the multiple cell, which is the linearized version of the groundwater model for the Sacramento Valley. So we have 7 subregions and build them in as linear constraints. And then, of course, moving on to CVSIM3, we now have the groundwater module of C2VSim built into CVSIM3. Going back now to the early 2000s, the CalFed peer review of CVSIM2, and there were, I think, 5 gentlemen in the peer review. I think it lasted 3 days or 4 days. On the last day, I was supposed to give a presentation where I was going to outline how I'm going to link C2VSim or CVGSM with CalSim. And everybody said, no, we don't want to deal with another groundwater model, we're running late. But one of the gentlemen, who's Peter Laux, who's a professor at Cornell University, he mentioned something, and he says, why are you trying to link the CVGSM or the C2VSim with the systems model? Why don't you just create one model where you let the simulation model do all the routing and the hydrology part, and let the systems model just do the thinking of what the reservoir release is, what are the diversions, and the groundwater pumping. And I said, that's going to be the basis of my dissertation. So, moving forward, again, I want to acknowledge Jay Lund. Actually, I want to acknowledge first Dr. Miguel Marino, who passed away. Actually, all the work was done with him. He passed away a little over a year ago. But I again want to thank Jay Lund because really instrumental in getting me to finish the PhD, wrap it up. And of course, I want to thank the Department of Water Resources and all the supervisors and management for supporting me while I was working there. I want to highlight the disclaimer that you see here. So this is a presentation from a PhD research. It does not imply that this is what DWR is doing right now, nor does it imply this is where DWR is going. So that decision has to be made at a later date. So right now, CVSIM3 is our official model for the department. We do have the groundwater module of C2VSim built into it. In addition to that, the version of C2VSim that I'm working with is actually the old coarse grid. So you heard a little bit about the fine grid and all the refinements that are going into it, all the complications. This is an older version of C2VSim. So my outline, I'm going to quick overview of C2VSim, then talk about modifying the C2VSim historical development, talk about a C2VSim projected level or current level of development, or what a base case, and then talk about the systems model, which is a whole new systems model of the Central Valley using the RIMS, called SIM2, and then linking the two with CVSIM. Unfortunate acronym, do not confuse it with C2VSim. This is CVSIM. There is no 2 in there. And then I've got two applications, whether we'll have time to go over it or not. One is a global warming sensitivity analysis, and the other is a conjunctive use study. Okay, so CVSIM is really about linking two models. A simulation model, C2VSim, which is driven by a WFM as the engine. A systems model, which is SIM2, that is driven by the RIMS. In addition to that, there's another part to the research, which is the closure term. For those of you who are not familiar with the closure term and the hydrology development process of DWR-SIM, I'm not going to be talking about today. I actually have another presentation tomorrow morning in the Integrated Hydrologic Model Development session. I'll be talking more about that. So it'll be built in there. The result will show it, but I'm not going to be talking about it. So again, the motivation is C2VSim computes all the hydrology, including the water demands, precipitation runoff, stream aquifer interaction, bypass flows, including weirs, adjustments, and passes it on to SIM2, which is the systems model, and compute reservoir releases, surface water diversions, and groundwater pumping. So essentially, CVSIM really are two models linked together into one model, and there's communication back and forth, variables that pass from one to the other. So I'm not going to talk about C2VSim. I think we've talked about enough about it. You know, this is the course grid with all the three layers, the nodes, the streams, and the types of land uses. And the simulation period is now 1922 through 2003. At the time I did the research, we had not extended it through 2015. Okay, so this is really the 21 subregions of C2VSim. And I'm just going to show a couple of areas. So this is depletion area 58, or subregion 1 and subregion 2. You have the Sac River, minor streams coming in. You have imports, local diversions. You have exports, and you have bypass flows. Here's another one of the Delta area. So you have the American River Basin, and then depletion area 65, or subregion 6, the Delta, and the East Side Streams area. And again, I will talk about the exports that are actually built into C2VSim also, and then we have the Delta outflow. All right, so the first thing was to compile the subregional historical outflows, use C2VSim to compute the historical adjustment. What are the adjustments? Adjustment, if you take a simulation model like C2VSim and you look at the stream outflow of each subregion and you compare it to observed outflow, there are going to be differences. So that's in a way what we call the closure term in the hydrology development process. So you can do a water budget historically, and the difference between that water budget to compute the outflow and the simulated outflow is the essentially the adjustment. So what we did in the old hydrology development process, we build that back in as a water supply, and it accounts for either streams that are not measured, diversions that were not modeled, and a bunch of other parameters. Again, I'm going to talk about developing an ANN, artificial neural network, for each subregion as a function of 14 variables. This was built into C2VSim, what I'm going to be talking about today, but this we'll be talking about more tomorrow morning. I also modified C2VSim so that now the weirs, the Molten Colusa, Tisdale, Folsom, and Sacramento weirs are actually modeled in C2VSim, not in the systems model, and it gets passed to the systems model. And then integrate both of these into the historical C2VSim run. Okay, next I'm going to talk about a projected level land use. So this was all the historical run. The next one is the projected level. At a projected level land use, and I'm going to use like the 2003, circa 2003 as the current level of development. Started out with all the DWR surveys that are available online. Made a lot of corrections. If you've noticed, some of them have a lot of corrections in the attributes, mosaicked it, and then aggregated to the subregional level. That gives me then the aggregate, the crops, 14 different crop categories, native vegetation, riparian, for each of the 21 subregions. Then we need to deal with the projected level boundary stream flows. These came from two different sources. One is calcium 2 run for the State Water Project Delivery Reliability Report from 2009. And the other one, if it was not available here, I took the historical C2VSIM run, took the period 25 to 2003, kind of the recent, with all the projects in operation, did a monthly average, and then separated up into water year type. Projected level diversions comes from either these two, from this calcium 2 run or the historical, or also work that was done by C.H. Tom Hill as part of the common assumptions for CalFed for storage investigations. And finally, groundwater level pumping. So that is usually the closure term in C2VSIM, because we really don't know what the groundwater pumping is. So you run C2VSIM with all this built in, and you turn the adjustments on, and that gives you the groundwater pumping to balance the supply and the demand. SIM2. So this is the reservoir simulation model. Why do I call it SIM2? Because I had a SIM1 that was only the Sac Valley, and I say, why stop there? So I did the whole Central Valley. So it was set up as a model, set up as a mixed integer linear programming problem, which is similar to what calcium 2 and calcium 3 is. It simulates the operations of selected reservoirs to calculate the releases and the allocation, which is both diversions and groundwater pumping. The time series of the runoff, return flow, stream-active interaction, bypass flows, and the adjustments would come from C2VSIM. I'll explain that in another slide. This is only a PhD, so I only modeled Sacramento Valley, took the 4 reservoirs, Shasta, Oroville, Folsom, and San Luis, both CVP and SWP. The remaining reservoir releases in the San Joaquin and Tulare come from other sources, specifically the C2VSIM projected one. So it either came from a calcium 2 or from the historical. The operations in the SIM2 were only minimum. Again, this is a research project. So I only took the flood control diagrams were built in, selected minimum in-stream flow requirements, SAC, feather, and so forth, and then built in the COA, and then the import-export ratio for the delta. The underlying assumption here is try to create a simplified systems model as possible. So leave all the complications to C2VSIM, simplify it in the systems model, because it only needs to do the allocation part of it. I'm simplifying it here. It's much more complicated than that. For those of you who know, I'm not even dealing with the cycles here, so let's keep it at that level. And finally, and then the waste and the allocations, again, are supposedly by priority, driven by priority needs. Okay, so this is the, again, the subregions into, for SIM2. So here's the north of the delta. There are 4, then there's the south of the delta. This is all going all the way from Shasta down to Bakersfield. And this is just a couple of diagrams showing the spaghetti schematic that you see. Again, this is a very simplified version of the systems model. Again, you have the now inflow with the reservoir being operated. You got evap. Then you have local diversions. You may have imports. And then you have the diversions to meet the demands. And then you have exports to other subregions. So here's north of the delta, and this is one from south of the delta. Kind of gets really complicated, but the point being is it includes all the exports from the delta, both to meet demands within the Central Valley and then the exports to Southern California. So linking the two, C2VSIM and SIM2, is an iterative process. And actually what I found out is you can actually run C2VSIM, and then you can run calcium, run SIM2. Again, there's variables that are exchanged between the two. These are the variables. Let me start with the variables. So there are 84 variables that are passed from C2VSIM to SIM2. These are all the demands, the runoff, the return flows, the seepage, and the adjustments. 80 variables that are passed from SIM to C2VSIM. These are all the diversions and the groundwater pumping, reservoir releases. And then there are other miscellaneous 29 variables. Convergence is reached, essentially, it's an iterative process. Convergence is reached when the variables pass the successive iterations, the differences become negligible. And what's quite surprising is kind of a simplified model, at least on the system side, but the convergence never went more than about 6 iterations, 6 or 7 iterations at most. Okay, so now, and my time is almost up. So I'm going to quickly go to the two studies. One is a global warming sensitivity study, and then the other one was a conjunctive use study. Essentially, in the global warming study, what was done was look at the 4 reservoirs, Shasta, Oroville, Folsom, and built in the changes in temperature, because we expect temperatures to change by up to 4 degrees at the end of the century. Actually, it could even be more than that. And then focus on what the impacts are. There are 2 major impacts that you will see over here. One is that because of increase in temperature, the increase in demand will increase. ETCs for the crops will increase. I have here the procedure, whether I did that, I'm not going to go through that. And then this will modify also the inflows into the Orvilles that I mentioned. So here are just some of the results that you will see. Here is the impact on the ETOs, because ETC again is ETO times K sub C. ETO is potential ET, K sub C are the crop coefficients. So the ETOs, which is really what came, which is really what is changing, and you can see the impact as you increase temperatures, of course, ETOs increase and therefore ETC increases. And what you'll see over here is the impact on the water demands on the ag supply requirement. So you'll see here, not so much in the winter times, but especially in the ag season, the higher the temperature, the higher the demands. These are just the impacts of the inflows into the reservoirs and how they change with the temperatures. And mainly, of course, because you now have snow melt that is earlier, so it shows up earlier into the reservoir, and you have less in the spring and summertime. Some of the results of CVSIM, here is the impact on the delta outflow. I'm sorry, these are the release. Now I'm comparing this all to the base. So when you see +1, +2, +3, +4, this is really the +1 scenario compared to the base. So this is the increase or decrease relative to the base case. So you see here the impact on the releases of Oroville, Folsom. These are the exports that you see in the delta. Again, the impacts are shown there. Again, if you really want to get into this, all the details, if you have a weekend, read my dissertation. It's available online. Here's the monthly increase in surface water diversions. Again, higher demands, higher surface water diversions, because diversions are the first source of water before you close it with the groundwater pumping. And then the impact on groundwater pumping is down here. Again, significantly higher. By the time 4 degrees, you increase it by 4 degrees, it can increase to about 350 TAF. And this is Central Valley-wide. In terms of impact on groundwater storage, things are declining as it is, but this is really complicated with the temperature increases. This is impact on the storage, and here as you see the long-term impact. Again, this is the base case over here where it's already declining, but superimpose on that the increase in temperature, and you'll see it exacerbates the problem. The next one is the Sacramento Valley Conjunctive Use Study. It's a conjunctive use program. And it actually, back in 2000, I think there was a settlement. This is all part of phase 8 of the control board hearings related to D1641. What came out of that was the Sac Valley Water Management Program, where about 30 stakeholders in the Sacramento Valley would forego their surface water rights, their diversions, diverting nearly 187 TAF in not wet years, which is below normal, above normal, dry, and critical, and in the months of June through September, and instead pump groundwater. So they forego their surface water diversions, pump groundwater. The expected decrease in diversions, that's the expectation, was that decrease in diversion would then show up in the delta. So then the projects can either operate the reservoirs, delta outflow, or exports. And in addition to that, the expectation was that the groundwater elevations would recover so there'd be no long-term impacts. Key question is, how much of that water actually reaches the delta? And what is the long-term impact of the project? Well, to make a long story short, what you see here, so what actually reaches the delta out of the 187 is only about 40 TAF. So, with all the qualification, this is an older version of C2VSIM. It has been recalibrated, so the numbers themselves might not be good, but at least they match actually work that Charlie did a few years ago when he used C2VSIM without any of the reservoir operations. Again, you see the same kind. I think what reaches the delta was, I don't know, which was probably higher than this. But again, this was what this one shows. And this shows what is the source of that data. And you'll see most of that source. So here's the reduction in the diversions. But again, the source of the data was mostly you lose it actually through seepage. In addition to that, by the way, what happens is when you cut back diversions, it increases the elevation in streams. When you increase elevation in streams and you're increasing groundwater pumping, that actually increases the gradient of seepage. And that explains partially what's happening over here. Okay. Well, I'm not going to go through some of that. I'll just move on. And then the important thing is really the cumulative impact over the long term. So here's on the project on groundwater. If you look at it over the long period of time, it really never recovers. And again, we saw that I think with Charlie, even though he had a shorter period of time. Here I'm modeling the entire 82 years. I think he was modeling 20 plus years. And you see it just continuously never recovers. Can you solve that? Yeah. Don't operate only in non-wet years. Operate only in, maybe in the dry and critical years, for example. So you have the above normal, below normal, and wet years to recover. This is another way of looking at where the water actually comes from that increased in groundwater pumping. And again, you see here that it mostly comes from seepage. So I think the answer to the two questions, in the long term, only about 20% of the cutback and diversion reaches the delta. The program is not sustainable as it is due to increased declines in groundwater storage and elevation. Okay.